Welcome to Theory of Computation. This is lecture number 10. In the last lecture, we discussed about the halting problem. We actually showed that the halting problem is one of those problems which we call undecidable. What that means is that you cannot make a Turing machine that can tell us whether a string is in the language ATM or not. Or more precisely, given a description of a Turing machine and a string, another Turing machine cannot tell whether that Turing machine will halt on that given string or not. The halting problem is a central undecidable problem. In fact, it's the first problem that we have proved which is undecidable. It's the first problem known to us that we have been able to show that the halting problem is undecidable. This problem is going to play an important role in the rest of the course, or at least the computability part of the course. The way we will show that other problems are undecidable is by reducing them to the halting problem. The idea is this. Suppose you have a problem and you want to show that it's undecidable. If you could show that if you can solve your problem, then you could also solve the halting problem, then you can conclude that the question given to you is also undecidable, because we already know that the halting problem is undecidable. How did we prove that the halting problem was undecidable? Well, it was actually a very clever and subtle argument given by Alan Turing. We went through that argument in detail last time. We looked at the proof, and then we opened up the proof, re-examined it, and realized that the proof of the undecidability of the halting problem is nothing but extremely elaborate diagonalization. So the underlying idea is diagonalization. That is the idea that we use to prove that the halting problem is undecidable. In today's lecture, this is what we are going to do. First, we will once again discuss the undecidability of the halting problem. After that, we will discuss an extremely interesting topic called Russell's paradox and see how it is related to the undecidability of the halting problem, to actually Turing's theorem. After that, we will look at the notion of reducibility. And then we will show several undecidable problems in language theory. In the end, we would look at linear bounded automata and show that some problems concerning linear bounded automata are also undecidable. Let's review the proof that the halting problem is undecidable. You must recall what the halting problem was. Remember, we had this language that we called ATM, which consisted of all pairs m, w such that the Turing machine M accepts the string W. So ATM is the set of all encodings of m, w such that M accepts W. So you can think about it this way. You're given a Turing machine M and input W, and you have to decide whether M will accept this string W or not. In other words, you're given a program and some data for the program, and you have to tell whether this program will output yes if you run it on this data, whether it will accept that data or not. That is the halting problem. We showed that the halting problem was undecidable. Let's have a look at this proof. This theorem says that the language ATM is undecidable. That is, there is no Turing machine H such that H on the input m, w will accept if m accepts W and will reject if m does not accept W. How did we prove this, that such a Turing machine H does not exist? We started by assuming that H exists and then reduced that to an absurdity. What we did was we started with this Turing machine H, and using H constructed a new Turing machine called D. Let's have a look at D. We use H to construct D. D converts its input M into the pair M followed by the description of M and calls H. It returns the answer that is the opposite of the one that is given by H. So the Turing machine D takes another Turing machine M or description of another Turing machine M and tells us whether M will accept its own description or not. If M accepts its own description, then D rejects M. If M does not accept its own description, then D accepts M. Well, once we have constructed this Turing machine D, we can ask the question, what would happen if we were to run D on its own description? When we ask this question, we realize that D will accept its own description if and only if it does not accept its own description, which is simply absurd. And this absurdity is a contradiction, and therefore our proof is complete. This contradiction allows us to conclude that the Turing machine H does not exist, because we started with the assumption that the Turing machine H exists, and from there took logical steps and reached an absurdity. Let's look at this argument once again. We know that H accepts M, W exactly when M accepts W. Therefore, D will accept the description of M exactly when M does not accept the description of M. So D accepts the description of M when M does not accept its own description. Now, what will happen if we run D on its own description? D accepts its own description exactly when D does not accept D, and this is a contradiction. So, this ends our proof. As you can see, this proof is not very long. It's a few lines, but it's extremely subtle. It's very cleverly crafted. That's why it took Turing such a long time to come up with this proof. This is actually a central argument in computer science. This is a very clever use of diagonalization to show that the halting problem is undecidable. Notice that we have already proved that the halting problem is Turing recognizable. What does that mean? Well, that means that there is a universal Turing machine U which takes M, W and it accepts M, W exactly when M accepts W. This universal Turing machine does nothing but simulate the behavior of the Turing machine M on the input W. When it does that, if M halts on W and accepts, U accepts. On the other hand, if M does not halt, then U does not halt also. So therefore, this shows that the halting problem is Turing recognizable, but we can prove that it's not decidable. Let's look at the last part of this argument. What we did was we created a Turing machine D that accepts all those Turing machines which do not accept their own description. Now we can ask the question whether D accepts its own description. When we ask this question, we realize that D accepts its own description if and only if it does not accept its own description. Well, I want to talk to you now about Russell's paradox. Bertrand Russell was a philosopher, an extremely famous and great philosopher who wrote a lot of books on mathematics as well as on philosophy, and he came up with a paradox in set theory. We would not study Russell's paradox in set theory, we would just look at a toy version of it, which he used to popularize his paradox. His paradox goes as follows. A man in Seville is shaved by the barber of Seville if and only if the man does not shave himself. So Russell says that there is a town called Seville in which every man who does not shave himself is shaved by the barber of Seville. So the barber of Seville shaves exactly those people who do not shave themselves. Well, once Russell presents us with this situation, he poses the following question. Does the barber shave himself? So the question that arises is, does the barber of Seville shave himself? Well, if we try to answer this question, we realize that the barber of Seville shaves exactly those people who do not shave themselves. So the barber will shave himself if and only if the barber does not shave himself. And that's absurd. And from there, Russell concluded that there cannot be any such barber who shaves exactly those people who do not shave themselves. So this is Russell's paradox, or this is a toy version of Russell's paradox. A barber who shaves exactly those people who do not shave themselves, such a barber cannot exist because that leads us to an absurdity. We can try to understand this kind of an argument by another example. Let's say that you are sitting in a classroom and your teacher asks you to write down a list in which you are allowed to put names of any students that you feel like. And you can include your own name or not include it, it's up to you. So we have a classroom in which everybody on a piece of paper writes down any list of students that they feel like in the classroom. Including themselves, they can choose to include their name on the list or not. What we can do is we can ask the following question. Is there one particular student who wrote the names of exactly those people who did not include their own names in their lists? So we're looking for a student who will make a list which happened to coincide in this situation in the following way. This list consisted of the names of all those students who did not put their own name on their own list. Can such a student ever exist in a classroom, or can a situation like that arise? Well, suppose such a student exists and that student is S. You can always ask the question whether the student put his or her own name on his or her own list. Well, if the student did put their name on their own list, then they did not. And this leads to a contradiction. So this is another example of this kind of an argument in which we ask the question, did the student put his own name on his list? And we reach a contradiction because the student did, if and only if he did not. Let's look at another example, which is from computability theory. Let's consider the following problem. We have studied enumerators. Enumerators are Turing machines. Recall, enumerators are machines like Turing machines which do not take any input. When we turn them on, they start writing output on an output tape. They write one string after another, and so on and so forth. So suppose I ask you that you run an enumerator. You can run the enumerator and look at its output and see if that enumerator ever enumerates its own description. Some enumerators would enumerate their own descriptions, others would not. There would be some enumerators that don't enumerate their description at all, and there are other enumerators that would. Now the question is, can you ever construct an enumerator, or can an enumerator exist which enumerates all the description of all those enumerators that do not enumerate themselves? Is it possible for an enumerator to enumerate the description of all those enumerators which do not enumerate themselves? Well, you hypothesize that such an enumerator F exists. Now you ask the question, would F enumerate its own description? When you try to answer this question, you realize that F will enumerate its own description if and only if it does not enumerate its own description. And this once again leads us to conclude, this contradiction leads us to conclude that such an enumerator cannot exist. So there cannot be any enumerator that enumerates the description of all those enumerators that do not enumerate themselves. Let's look at these 4 examples that we have looked at. We came up with this Turing machine D that accepts the descriptions of all those Turing machines that do not accept their own description. In the second example, we have a barber who shaves all those people who do not shave themselves. In the third example, we have a student who writes down the names of all those students who don't write down their names. And in the last example, we have an enumerator that enumerates the description of all those enumerators that don't enumerate their own description. In all cases, we can conclude that such objects cannot exist In the first case, we simply ask the question, does the Turing machine D accept its own description? And we realize that D accepts its own description if and only if D does not accept its own description. On the other hand, in the second case, we realize that the barber will have to shave himself if and only if he does not shave himself, which is once again an absurdity. In the third case, we realize that the student would have to write down his or her own name if and only if he or she does not write down his or her own name. Once again, an absurdity, so such a student cannot exist. In the last case, we realize that the enumerator F will have to enumerate its own description if and only if it does not enumerate its own description. So all these examples are of a similar kind of argument which show that these objects cannot exist. The subtle thing about proving the halting problem is that the halting problem itself does not fall into that category. We use the halting problem, we assume that the halting problem is solvable or decidable. If we assume that, then we can conclude that D exists. But this argument tells us that D does not exist, and we reach an absurdity. Therefore, we can conclude that no Turing machine exists that can solve the halting problem. No decider can solve the halting problem, and therefore the halting problem is undecidable. The proof of the undecidability of the halting problem is of course very subtle and involves a clever diagonalization. However, once we have proved that the halting problem is undecidable, we can use this fact to show that other problems are also undecidable. Suppose you have a language B in your mind, and suppose you can say the following statement. You can say that if I could solve B, if I could make a decider for B, then I could also make a decider for the halting problem. Well, then you can immediately conclude that B is undecidable, because we know that the halting problem is undecidable. Suppose someone claims, if I could find a decider for a language B, then I can use it to make a decider for ATM. We can then conclude that B is also undecidable, as we know that ATM is undecidable. This technique is going to be called reducibility, and we will use it to show that there are other problems which are undecidable. In fact, when we use reducibility, we won't have to do as much work as we did before, and these arguments are going to be relatively straightforward. Let's look at an example. Let halt Tm be the set of all pairs m, w such that the Turing machine M halts on W. Notice that this problem halt Tm is slightly different from ATM. ATM was the acceptance problem. You were given a Turing machine M and W, and we had to tell whether the Turing machine M accepts the string W. This problem is slightly different. We're given a Turing machine M and a string W, and we have to decide if M will halt on this string W or not. So this is a slightly different language. The theorem we would prove is that halt is undecidable. So we're going to show also that this problem is also undecidable. So it cannot be decided by a Turing machine. The rough idea is as follows. If you think about ATM, in ATM we have to tell if M accepts W, and we have to, if we want to prove ATM is undecidable, we want to make a decider which tells whether M accepts W. ATM is not decidable. However, we have shown that ATM is Turing recognizable, and that we showed by just simply saying that there exists a universal Turing machine. The universal Turing machine simply simulates M on W. The reason that the universal Turing machine does not always halt is because M may not halt on W. Now suppose somebody could tell us whether M will halt on W or not. Then what we could do is first find out whether M halts on W. If it does not halt on W, then we know that M does not accept W. and so we could simply say that M does not accept W. On the other hand, we find out that M halts on W, then we can run the universal Turing machine on M comma W to find out whether M accepts or rejects W. So this way, if somebody gives us a Turing machine that decides halt Tm, we would be able to make a Turing machine that decides ATM. Let's have a closer look at this proof. Suppose that halt Tm is decidable. Then there is a Turing machine R such that R of M comma W is going to be accept if M halts on W. It's going to be reject if M does not halt on W. So R is going to be quite an amazing machine. Given a Turing machine M and W, it will be able to tell us whether M will halt on W. If M halts on W, it will say accept. If M does not halt on W, it will say reject. Furthermore, this Turing machine R will itself always halt. If such a Turing machine existed, that would be very useful, because if we run a program and we on certain data and we are not sure if our program has bugs in it or may run into an endless loop, we could run R on our program and data and find out if our program will halt. Of course, such a program doesn't exist, and that's exactly what we are trying to prove. So let's go on with the proof. Suppose if we had R, we would have no problem with our programs running endlessly. We could always check if they would. We can use R to make a decider for ATM. Since we know that ATM is undecidable, therefore we have a contradiction, and therefore we conclude that R doesn't prove. How do we use this Turing machine R to make another decider for ATM? Well, let's call that decider S. Here is a description of that decider. The input to this decider, of course, is going to be a string M comma W. This decider will run R on M comma W. If R rejects, then decider will reject. If R accepts, only then will this Turing machine S simulate M on W. If M accepts, it'll accept, and if M rejects, it'll reject. So in this case, let's see what S will do if we were to give it a string M comma W. Suppose we give S M comma W, it will reject if M loops forever on W. So it will simply reject all the strings M comma W in which M loops forever on W. Suppose that M rejects W, S will also reject these strings. And it will only accept those strings in which M accepts W. It will only accept M comma W if M accepts W. And S always halts. So the language of S is ATM, and S is a decider. This shows that S is decidable. That's a contradiction. Well, how did we reach this contradiction? Let's think about it. We made this new Turing machine, this decider for ATM, which was called S. This decider was using R, whose existence we assumed. We assumed that R exists, then we proved that S exists, and then we showed that S will be a decider for ATM, which is absurd because we already know that ATM is undecidable, therefore R cannot exist, and therefore our original problem, halt TM, is not decidable. As you can see, this proof was not very difficult. The reason this proof was not difficult, or at least not conceptually difficult, because we did not have to go through diagonalization over again. All we had to do was simply argue that if there were a Turing machine that was solving the problem halt TM, we could simply use it to make a decider for ATM. So we showed that ATM could be reduced to solving of this problem halt TM, and therefore that problem must be undecidable. Let us use reducibility to show another problem is undecidable. Right now we are concentrating questions about Turing machines. We are looking at problems that concern Turing machines. So usually we are asking the question whether a given Turing machine will accept a string, or whether a given Turing machine will halt on a string, or things like that. The new problem we are going to look at is called the emptyness problem for Turing machines. So this language consists of all those descriptions of all those Turing machines whose language is empty. So we will be given a description of a Turing machine, and we have to tell if this Turing machine does not accept any strings. Notice that previously we had been asking for what a Turing machine does or how it behaves on one string, whereas this emptyness problem is in some sense asking about how a given Turing machine behaves on all strings. If a Turing machine does not accept all strings, then that should be accepted. If a Turing machine accepts at least one string, that Turing machine should be rejected. So if we think about it very superficially, emptyness problem seems to be a much harder problem than the halting problem. It also seems to be a much harder problem than the previous problem we saw, because it's concerned with the behavior of a given Turing machine on all possible strings. Therefore, we can superficially say that this problem seems harder. But can we actually prove that this problem is undecidable? Well, what we can do is we can assume that this problem is decidable, and then try to show that we can take a decider for this problem and use it to solve ATM, use it to come up with a decider for ATM, which would be absurd, and therefore we can conclude that this problem is undecidable. Suppose ATM is decidable, then there is a decider R such that R on input the description of M will accept if the language of M is empty, and it will reject if the language of M is non-empty. How can we use R to construct a decider S for ATM? Can we use a decider which tells us whether the language of a given Turing machine is empty or not to solve ATM, to come up with the decider S for ATM? Well, let's try a naive idea. What we can do is S gets a pair M, W and has to decide if M accepts W. So what S can do is run R on M. Now if R accepts M, that would mean the language of M is empty, so surely W is not accepted by M. Hence, in this case, S can simply reject the pair M, W. However, if R accepts M, then S knows that R accepts some strings but doesn't know whether it accepts W or not. So this idea doesn't seem to work. So we have to come up with a more clever way. See, what happened is we said we get the pair M, W, we can ignore the input W and find out if the language of M is empty. If the language of M is empty, then M is not going to accept W. On the other hand, if the language of M happens to be non-empty, then we know that M accepts some strings, but it doesn't give us any information about W. And therefore, this idea doesn't seem to work. Can we use a cleverer idea so that we can use this decider, this hypothetical decider R for this language and use it to come up with a decider S for ATM? Well, yes, there is a cleverer idea. Let's have a look at it. Let's say we are given a pair M, W. Suppose we construct a new Turing machine M1 as follows. On input X, this Turing machine will compare X and W. If X is not equal to W, it will reject. If X is equal to W, then it will run M on W and it will accept it if and only if M accepts. So what is this Turing machine M1 doing? What it does is it has W hard-coded in it and it has M also hard-coded in it. When its input comes, it just compares it with W, and if there is no match, it simply rejects the input. If X matches perfectly with W, then it runs M on W, and if M accepts, it accepts. So what is this Turing machine M1 doing? And can we build it by looking at M and W? Well, it's very easy to make this Turing machine by looking at M and W. M is a subroutine in this Turing machine, and the other part of this Turing machine is simply matching of two strings, which we know how to do. Therefore, by looking at M and W, we can construct M1. In fact, we can make a Turing machine which can take M, W and output M1. So there's no problem in constructing this Turing machine M1. But what's the language of M1? Let's have a look. What can we say about L of M1? Well, L of M1 is going to be just the single string W if M accepts W. And it's going to be the empty set if M does not accept W. So we can say that the language of M1 is non-empty if M accepts W, and it's empty if M does not accept W. So the question whether M accepts W or not is the same question as whether the language of M1 is empty or not. And therefore, we can use R to answer this question. Let's look at a more formal solution of this problem. Now we are ready to describe our decider S. On input M, W, we use M and W to construct M1. We run R on M1. If R rejects, we accept. If R accepts, we reject. So in this case, S will accept M, W if and only if the language of M1 is non-empty. However, the language of M1 is non-empty if and only if M accepts W. Hence, the language of decider S is going to be ATM. So we've found a decider S for ATM, but we know that ATM is undecidable. And therefore, this leads us to a contradiction. Hence, we conclude that R does not exist, which means that the emptiness problem is undecidable. Once again, we have used reducibility to show that the emptiness problem is undecidable. Let's look at the overview of this argument. The overview goes as follows. We said if we could decide the emptiness problem, if we could find a decider for the emptiness problem, we could use that decider to come up with a decider for ATM. Now, since ATM is undecidable, therefore the emptiness problem must also be undecidable. Let us look at another problem which is undecidable. This is called the regularness of Turing machines problem, the regularness of TM problem. Regular TM is the set of all encodings of Turing machines M such that M is a Turing machine and L of M is regular. Well, let's try to understand this problem. The input to this problem will be a Turing machine M. If this Turing machine accepts a regular language, then we have to accept this input, and if this Turing machine does not accept a regular language or accepts a non-regular language, then we should reject this input. That's what would mean for regular TM to be decidable. What we want to show is that this problem is undecidable. You have to be a little careful. Suppose if I were to change this language a little bit, suppose if I were to tell you that I'll give you a description of a DFA, and you have to accept all those DFAs whose language is regular, then the problem would be trivial. Because we know that DFAs accept regular languages. In fact, that's a characterization of regular languages. However, the problem is highly non-trivial for Turing machines. A Turing machine may accept a regular language or it may not accept a regular language. So, in this case, we want to collect all those Turing machines that accept a regular language. What we will show now is that this problem is also undecidable, and once again, we will use the same trick that we have used in the previous two examples. What we will do is, we will show that if this problem were decidable, then ATM will also be decidable, which would be a contradiction. Let's look at the proof. We suppose that regular TM is decidable. We will use the decider for regular TM to construct a decider for ATM. But we know that ATM is undecidable, and this contradiction will end the proof. Suppose that regular TM is decidable. Then there is a decider R such that R accepts all the descriptions of those Turing machines which accept a regular language, and it rejects all other descriptions of Turing machines. how can we use R to construct a decider S for ATM? Note that S gets an input M, W and has to decide if M accepts W. The idea is, as before, to construct a new Turing machine M2, which will now depend on M, W, such that L of M2 is regular if M accepts W and it's not regular if M does not accept W. Can we come up with such an M2? So the idea is you're given a Turing machine M and a string W. What you want to do is, by looking at M and W, come up with a new Turing machine M2 which has the following property. Suppose that M accepts W, then the language of M2 should be regular. On the other hand, if M does not accept W, then the language of M2 should not be regular. Let's look at a description of this Turing machine M2. Let us say we are given M, W. Now we construct M2 as follows. On input X, if X is of the form 0 to the n, 1 to the n for some integer n, M2 is going to accept X. If that is not the case, then M2 will run M on W, and if M accepts W, M2 will accept X. Note that W and M are once again hard-coded in M2. It's very easy to come up with the description of M2 if we are given the strings M and W. Let's look at what the language of M2 is going to be. Well, suppose that M does not accept W. In that case, M2 is going to only accept strings of the form 0 to the n, 1 to the n. As we all know, 0 to the n, 1 to the n, that language is not regular. On the other hand, if M accepts W, then M2 is going to accept all strings, all X's which are given to it as inputs. Therefore, the language of M2 is going to be 0, 1 star, this set of all strings over 0, 1. And in that case, it's going to be regular. So what we have done is we have succeeded in coming up with a new Turing machine M2 by looking at M and W, such that the language of M2 is not regular if M does not accept W, and the language of M2 is regular if M accepts W. Therefore, we can now use a decider for regular TM to construct a decider for ATM. Let's look at this decider in detail. We describe this decider S as follows. On input M, W, we use M and W to construct M2. Now we run R on M2. If R accepts, we will accept, this decider S will accept. If R rejects, then this decider S will reject. Thus S accepts M, W if and only if L of M2 is regular. However, the way we have constructed M2, L of M2 is regular if and only if M accepts W. Hence, the language accepted by this decider is exactly ATM. Notice that S halts on all inputs because R halts on all inputs. Therefore, S is a decider. This contradicts the fact that ATM is undecidable. Therefore, we can conclude that regular TM is also undecidable. So far, we have been using one line of reasoning. What we are doing is we're taking a problem and we're saying this problem is undecidable, and the argument goes as follows. We say that if this problem were decidable, we can use a decider for it to come up with a decider for ATM. And since we know that ATM is undecidable, therefore this problem is also undecidable. Let's go further and let's look at another example. So far, we have been using our pet problem, ATM, to prove that other problems are undecidable. Well, let's do a different example now. This is what I call the equality problem for Turing machines, EQTM. And it consists of encodings of pairs of Turing machines M1 and M2, so that M1 and M2 are Turing machines, and the language of M1 is exactly equal to the language of M2. You can think of this problem as follows. You're given two Turing machines and you have to tell if these two Turing machines are going to accept exactly the same strings. Well, this problem seems difficult because, as you know, number of potential inputs to a Turing machine is infinite. And in this case, you're given two Turing machines and you have to tell if the language of these two Turing machines is exactly the same or not. So this problem looks difficult, and on the surface we can say that this looks like an undecidable problem. But we simply cannot say that because a problem looks difficult, it is undecidable. We have to actually prove that it's undecidable. The way we will prove EQTM is undecidable is we will assume by saying that let's assume that this problem is decidable, which would mean that we have a decider which can tell if the language of two Turing machines is exactly the same or not. We will then use this decider to come up with a decider for ETM, the problem that we studied a little bit before, which was the emptiness problem. So we would say that the equality problem for Turing machines, if it is decidable, that implies that the emptiness problem for Turing machines is also decidable. But we know that the emptiness problem for Turing machines is undecidable, therefore we will conclude that EQTM is also undecidable. Let's look at the proof. Suppose that EQTM is decidable. Then there is a decider R such that R, when it's given a pair of Turing machine, it accepts if the language of these two Turing machines is the same, and it rejects otherwise. How can we use R to construct a decider S for ETM? In ETM, we have to tell only if the language of one Turing machine is empty, whereas R is actually telling us about two Turing machines. It actually can tell us whether the language of two Turing machines is the same or not. What we want to do is make a decider S that gets a Turing machine M, and it has to decide if the language of M is empty or not. Let's look at a formal description of this decider S. Notice that it is very easy to make a Turing machine M sub E such that the language of M sub E is empty. You can very simply design a Turing machine that rejects all inputs. It can, without reading, without scanning the tape, just simply the first step it takes is to reject the input. The language of such a Turing machine is going to be empty. We call that particular Turing machine ME, and you can design it once and hard code it. Now, let's look at the description of S. On input M, what S does is it runs the Turing machine R on the pair M, M sub E. And if R accepts, then it accepts. So, when does R accept the pair M, ME? Well, when the language of M is equal to the language of ME. But ME is the Turing machine that rejects all inputs. So the language of ME is empty. Therefore, R is going to accept the pair M, ME only when the language of M is empty. So the Turing machine S takes M and runs R on M, ME and accepts if R accepts. So Turing machine M is going to accept M if and only if the language of M is empty. Now if R is a decider, then S is a decider. If R halts on all inputs, then S is going to halt on all inputs. So if R exists, then and R is a decider, then S would be a decider for ETM. It will solve the emptiness problem for us. But we have already shown that the emptiness problem is undecidable. Therefore, we conclude that R cannot exist, which means that the equality problem for Turing machines is also undecidable. Well, we have discussed several problems which are undecidable for Turing machines. And basically, our argument was that we started with this one very important problem called the halting problem. We showed that this problem is undecidable using a very clever idea of diagonalization, a very subtle proof. Once we have shown that one problem is undecidable, then it becomes very easy for us to show several other problems, similar problems are undecidable. All we do is argue that if these other problems were decidable, then we'll be able to make a decider for ATM, which is impossible. And therefore, all these other problems are also undecidable. However, all the questions that we have looked at so far have to do with Turing machines. So we start wondering if there are other problems from other areas like graph theory or other computational games or other problems which are also undecidable. Are only questions about Turing machines undecidable? Are only languages that are concerned with properties of Turing machines are undecidable? Are there other languages which are also undecidable? Well, we will slowly move towards problems which are very different. They, on the surface, don't seem to have anything to do with Turing machines, and they are undecidable. Next, we will look at problems concerning some things called linear bounded automata. So linear bounded automata are just like Turing machines. They have an input tape and they operate just like Turing machines operate, except for they do not have any work tape. Furthermore, they are restricted to using the input tape as their work tape. They are not allowed to use any further space. So you can think about a linear bounded automata as a Turing machine which has an input tape, and you give it the input and you chop off the tape. So it is not allowed to have an infinite tape. It only has as much tape as the input. So if the input is extremely long, then it has a lot of tape. However, if the input is really short, then it has very little space to work on. These machines are called linear bounded automata. Linear meaning they only take as much space as is linear in the size of the input. What about questions concerning linear bounded automata? What if somebody asks us whether a linear bounded automata accepts a given string or not? So what about the acceptance problem for linear bounded automata? Or what about the emptyness problem for linear bounded automata? Are these problems decidable or undecidable? Later, we would look at post-correspondence problem, which is a problem that does not seem to have anything to do with language theory. It does not have anything to do with Turing machines or context-free grammars or linear bounded automata or any kind of automata. It is simply a puzzle. It's one of those problems that you look at and you say, this looks like a very simple puzzle. We would show that the post-correspondence problem is also undecidable. So the theory of undecidability is extremely interesting. Many important and interesting problems are undecidable. Unfortunately, we will not be able to prove Matisevich's theorem in this course, which says that the language which is the set of all Diophantine equations that have integral roots is also undecidable. However, we would be able to prove that the post-correspondence problem is undecidable. So in some sense, we'll get a flavor of how undecidability proofs are constructed. I'll see you next time. Thank you and goodbye.